think he's here.
Okay, well, let's see if you can see us.
Hopefully, I mean, we can see us. That's
Hey,
a good
y'all.
sign.
Howdy.
Oh no,
Can't
is the speaker not working?
Oh, try and go on mic arrow.
Yep.
Yeah.
I will
No,
keep saying
actually-
things so you can try to hear something. I'll
Oh.
give some words.
Oh,
blah, blah,
okay.
blah, blah, blah,
Can you see us?
Can you?
Yeah, I can see you guys. Hey. That's awesome.
How's it going, Thomas?
Doing all right. Sorry for the delay.
Oh,
See it-
all good.
See if my
Just
camera
fine.
works. There it goes.
There
Oh. Cool. Yeah, how many people are in there? What are we looking at? Like 15, 20?
Yeah. I think 21, including me. That's pretty good
Nice.
numbers.
That's
Plus a
pretty
couple
good.
people online. That's really good.
Yeah. Howdy, online
Yeah.
people.
Okay, so are you prepared to like start your presentation? If you are, I can kind of introduce and then we can get started and you can introduce yourself.
Yeah,
Up to you.
go for do a little intro of tying all these presentations together, and then I'll kick it off if you want to make sure you're recording it and all that kind of stuff.
Yeah, we're recording, so I'll do that real
Cool.
quick and then we'll all be ready to go. So some of you have already heard this bit, but hey everybody, I'm Elizabeth. I'm president of the Rose Tech Radio Club on Rose's campus. This is the organization where we do experimentation with communications technology. So building antennas, building radios, experimenting with communications protocols. And basically this year we're trying to put together a series of professional talks to kind of like introduce students to the different kind of like aspects of this industry, because it's not very well known to students. We've realized, and there's a lot of opportunity here, and it's also just really cool. So we've got some really cool people coming in to tell us about what they work on and what they think is exciting. And this presentation is pretty cool because there's some exciting overlap with satellite and space technology, which I know quite a few people in here are into. So yeah, it should be a good talk. Take it away.
All right. Formal introduction. Hi. Hello, everyone. I'm Thomas Francois. Let me see how to get this to be full screened. So I am Elizabeth, and I talked a little while ago over Discord. She put out a call for people to offer to give talks, and I'm a student at Missouri S&T. I'm not going to restart my laptop right now. And so I think Elizabeth is also a amateur radio operator, so we kind of connected over that too. Can you guys see my screen intro slide? Cool.
Yes.
Yeah. So from one ham radio club to another, I'm coming from Whiskey Zero Triple Echo. I am on my master's right now at my school. I'm kind of in a weird part of my life. I work, so I do my master's thesis and things, and then work on my school satellite team, and then I'm also a Pathways intern through NASA Goddard Space Flight Center. I'm sure a lot of people are familiar with that. But for those that are not, it's basically a co-op, work while you're in school kind of thing, and then get exposed to real world NASA challenges, and it's a good time. Excuse me. So. I just wanted to help out and kind of pass along some knowledge of things that I've learned to you guys. Again, I'm still basically a student. I'm not going to say I'm, been doing this for 30 years or anything, but I've kind of found my little niche in radios and especially in aerospace applications. And so giving this presentation as kind of an intro. It sounds like a lot of you guys are part of a satellite team, Cubesat team. So this is probably not the most like groundbreaking for a lot of this stuff, but just hopefully I find that there's a large lack of knowledge in the comms part in particular, especially for spacecraft. In general, I think there would be more radio people, but for satellites especially. So I'm giving this presentation mostly to talk about the comm part, but a little bit of overview stuff.
Oh, you're muted if you're.
Ah,
Yeah, okay.
there it goes. Okay, wrong button. Okay, so yeah, typical disclaimer. This is just me talking. I'm not NASA, so don't sue me if you're thinking about it. So, but yeah, basically, I would like to introduce sort of like, like I said, just particulars about spacecraft design for like comm systems for spacecraft, a little bit about different antennas you might think about. I'll try and explain a little bit about link budgets because I know that's kind of a black magic scary thing to people, and also kind of give some examples of things that I thought were kind of interesting now that I've kind of learned some more, especially about like radiation effects and thermal effects, things that I would never have considered affecting a radio system. So, yeah, this should be fun. Let's see what happens. Um, so yeah, first big takeaway that I want everyone to have is space is really hard. I don't know why that's so like people don't seem like they understand that, but space is really freaking hard, and it's kind of why I've gotten into the aerospace field as an electrical engineer because I really just enjoy the like crazy engineering challenges that you have to face in space. Um, so a lot of times I go talking to other people who are not comm people. They usually kind of have this image in their mind of, oh, well, why can't you just put a smartphone on a satellite? I dropped it in a pool and my phone's pretty strong. It should work just fine. Or, oh, I heard your smartphone is so much more powerful than the Apollo 11 moon lander. Imagine, what you could do with a smartphone on a rocket. Sometimes people, especially in politics, talk about, why is space travel so hard and expensive? Why is it taking so long to get XYZ? We should be on Mars by now if something, didn't went a certain different direction. Um, and the phrase that I hope if there's anything my number one takeaway from this, I just hope none of you will ever say to anyone else on planet Earth, just slap a radio on it, because it's never that simple. I hope that's a thing you guys understand after this, because I hear that so often, that kind of underlying sentiment, and it's so much more than that. So, for example, I think a lot of people have this idea in their head about how comm systems on Earth work. Case in point, like your cell phone, you can walk around, make phone calls, send pictures, send data. It just kind of works. But there's a little bit of a reason for that. There's several reasons why it seems like it's that cell phones just work. Part of it is the challenges are just really not there compared to space. Cell towers are really big and heavy and really robust, put in the ground. They can take high winds and ice, not really a problem. In worst case, if something breaks, you can just go up there and work on it. Um, you're really not that far, maybe like across town. Worst case, nothing has to move. You just kind of put an antenna and it sits there. And also, your phone is really not ever gonna go more than like 100 miles an hour. Maybe if you're driving a little fast, it might. So let's compare that to space systems. There it goes. So in space, some nice numbers that everyone loves to see. Distance to the moon is, 238,000 miles away. Voyager 1 probe is 15.4 billion miles away. Even just in low Earth orbit, satellites are traveling like 18,000 miles per hour, right? This is like this is an entire different ball game to what people are used to on Earth. Satellites also just are such a tight engineering collage of problem solving that you can't change any one thing without everything else going wrong. So everything is on super tight margins. You've got the power that you have, and you can not spare anymore. And so you can't just put a bigger radio on it and hope something will work. It has to all be designed together. And your smartphone is not dealing with a vacuum. It's not dealing with super wide temperature extremes, radiation, and micrometeorites. I thought this was a neat fact. I didn't actually know this was the unit for this at the top. The Voyager 1 satellite is a 23-watt transmitter, which is actually pretty good for spacecraft. But because it's so far away, it is actually received at less than 1 attowatt, which is a billionth of a watt. One of my roommates actually just told me the other day, I'm not, it's not fact check, but it's something on the order of like 40 electrons is about, an attowatt. So it's really out there. So kind of let's start at the basics of if somebody comes to you and says, "Hey, I've got the satellite mission. What do I need to do for a radio?" One of the first things we talk about is what's called a link budget, and it's a good tool that RF engineers have to be able to just get a basic overview of a comm system. Just ballpark, is it even going to be close? So we're going to start with, satellite transmitter up here at the top, which has, some kind of power. It transmits energy, electromagnetic waves at some power, usually in watts. Yeah, you lose a little bit, cabling and stuff will heat up, that's fine. But then you have a really big antenna. It's usually as big as you can get it on the satellite. That gives you much better gain. Then you have to deal with, antenna efficiency and stuff. But then you have to deal with the long distance. Satellites are, like I said, never very close by. So you lose a lot of that energy just as it spreads out across the universe. You have to also take into account rain and atmosphere effects. You have to also account for polarization mismatch, which is a fancy way of satellite is pointed upright, ground station is pointed horizontally, and you lose some energy transfer there. You still got cables. You got to deal with cable loss. When it gets to your ground station antenna, luckily this helps you out. Having a really big ground station antenna with a lot of gain will help make that signal louder, which is really good. But again, nothing's perfectly efficient. You're never going to get the dish pointed exactly at the right spot. So that doesn't help. You can usually make the signal a little bit better with some filters. And there's a whole nother side of comm system that I am still a little bit new at, but you start to deal with thermal noise floor. So you have to think about like how hot is your receive radio, because all the electrons moving around inside of your electronics will basically make energy on your system that you have to make sure that you're louder than, kind of like TV static. And all of the, you can add a little bit of error correction too. That will sometimes help. And at the end of a link budget, we basically have to decide, okay, is this going to be enough for the mission to either work or not work? There is no right answer, which is, I think, it sounds like you guys are mostly engineers, so you've seen this too. There is never one right answer. And so you'll come across a lot of people that just say, oh, well, just put the biggest radio on that you can. And especially for spacecraft, that's usually not an acceptable answer, because it just has to work. If your antenna is a little bit bigger and your signal is a little bit louder, it doesn't really make your radio work any better. And your margins are as tight as they are. It really comes down to like all these little factors and what can we optimize and make better and decide these trade-offs for designing spacecraft comm systems. I don't think I need to explain this to you guys, but for those playing at home, Cubesats are if you hear that term, it is a class of nano and micro satellites that use a standard form factor. Think of it like a Rubik's Cube and just kind of start stacking Rubik's Cubes together. It really makes design, assembly, and launching these things a lot easier because as a common size, they can connect to launchers and deployers really easily. And so it's actually been revolutionary in the space industry in the last 10 or 20 years, just because of how many more organizations and companies and schools have gotten access to space now because you can make these cheap little satellites. We've already launched something on the order coming up on 3,000, and so many more will get launched at faster and faster rate as you start to get more access to space travel. So something else that a comm system engineer will also have to look at is the antennas. So there's a whole bunch of different kinds, but I'll kind of highlight some of the big ones and kind of like the things that you think about in your head when you go to design a mission. You start off with the basic. Everyone loves a dipole antenna. It's the simple one, just two pieces of metal cut at a certain length. They're really good for the fact that the satellite, usually when it gets deployed, is just spinning around all crazy. And the dipole pretty much radiates every direction, so no matter which way the satellite's pointing before it kind of gets its bearings, you can usually talk to it from the ground pretty easily. Not have to worry about pointing, but it's really low gain, and so you need to make sure you can get enough signal to that satellite if it has a dipole or monopole antenna. You could use a helix antenna, which has a bit better gain. Also comes the fact that it's circularly polarized, which lets you basically you don't have to care about how the satellite is oriented. You'll get the energy down. Um, no polarization mismatch as long as it's right hand and your receiver is right hand. But you start to get into a lot more paperwork, having to deal with something that's more complex and deploying off the satellite. It's heavier, it's more expensive, and you have to point the satellite back at the ground. So it doesn't work quite as well if you're just in kind of the detumble phase of your satellite mission. There's also patch antennas. These have really gotten more popular in recent years because as we go up in frequency, we can make these little tiny square patches act as antennas, and you can put a whole bunch of these patches together and make a bigger antenna out of small antennas, kind of summing up the energy collected by all these little receiver antennas. A single patch is usually pretty low gain, and a lot of times they take up one whole side, one face of a CubeSat, which usually would be reserved for solar panels. And again, you have to make sure that that side is facing the Earth, or if it's like a GPS antenna, it needs to be facing away from Earth. If you really needed to, you could try putting a dish antenna on a CubeSat, which has been done. I'll show a picture of RainCube on here, but it takes up a lot of space. It is really expensive, and you have to really make sure your satellite has good orientation, attitude control to point that dish back at Earth. But from all of that, you do gain a lot more gain, and so you're starting to see more of these types of antennas as CubeSats are starting to become starting to operate in cislunar or even within the solar system. CubeSats are starting to travel further, and dish antennas are kind of becoming more of a requirement just because stuff's going so far away. There's also two sides of the antenna link budget antenna equation. There's the flight side, and there's also the ground side. A lot of times, university teams especially end up using Yagi or helical antennas. These like repeated structures. It's basically a bunch of dipoles put together in an array. They're usually pretty light. You can make them out of tape measures if you wanted to. I'm sure you guys have done that. I think everyone in ham radio has done that at least once. But you can also.
Not everyone in this room has done that, but it is.
Oh, go fix that. That is a requirement. That is your homework. Get a tape measure Yagi build session and do a fox hunt. And you can buy these commercially, and even they're super common. They're not the best at really anything, but they're kind of an old reliable. They've been around for a long time. If you can, try and get a dish antenna, and this is typically what people do. The satellite is so hard to modify and make changes to that usually they make up for the link budget deficiencies by making a bigger ground station antenna. There's some people that have done their own dish antennas, but again, they're very heavy and it's hard to you get a lot into mechanics of actually pointing it and steering it and that sort of thing. Kind of for context, I'm putting this in here to kind of relate what you guys are doing in school to sort of how NASA works. And these are exactly the same challenges that they face, that you guys will face. But this is sort of how NASA, for those that don't know, kind of keep it organized. So I actually work for the NASA Near Space Network directly. So we have sites through Goddard. We have sites in White Sands, New Mexico, Wallops, Virginia, and a couple other groups that help us out. And we are in charge of things in mostly low Earth orbit. So like the Hubble Space Telescope and the International Space Station. That's kind of our bread and butter is, when you watch the astronauts, you're talking to them. That's usually coming through our system. Excuse me. Then you have the giant boys usually out in California or Madrid, Spain, or in Australia. These are the Deep Space Network dishes. These are mostly run managed through JPL, and they handle stuff like the James Webb Space Telescope, Voyager probe, the Artemis moon capsules, and even things like at Mars, all the Mars orbiters. Um, kind of as an outside perspective for you guys to have, NASA is actually working on what's called LEGS. It is the Lunar Exploration Ground Stations, and we're expanding the Near Space Network to kind of fill in the gap and kind of take over some of the missions between here and the moon. Because the Deep Space Network is, there's a lot of stuff happening here. Deep Space Network can only look at so many things at once, so pretty soon the goal is to try and hand over anything from L2 to the Earth, low Earth orbit, to the Near Space Network. There's a problem with this, and I'm, like we talked about before about how prolific CubeSats are, is now, I didn't do my little animation. Dang it. Well, the slide's supposed to just get full of CubeSats because there's so many satellites being put up every single day. This whole screen is supposed to be covered in CubeSats. That NASA really can't do it themselves. So it's especially now that universities are able to build satellites pretty easily. There's a lot more thought having to go into designing your own ground station to support your CubeSat missions because NASA can't take care of everybody on their own. So, for example, Morehead State they have 2 big dishes up in Kentucky. They actually launched Polar Ice Cube. It was a 6U CubeSat deployed off of Artemis 1 around the moon. That's what they use their dishes for. There's a school in Hawaii, for example, is probably like more average what a lot of satellite teams have. The Parkes Observatory in Australia also does CubeSat missions as well, like really far CubeSat missions. Stanford, University of Tasmania, just some examples. But sometimes the schools have to come together and play NASA ground station. Some stuff to want to talk about also for your knowledge. Part of what makes space really hard and you don't really deal with on terrestrial systems is that there's a lot of stuff in space that wants to kill your satellite. And one of the big ones for electronics is radiation. There's 3 main types. There's cosmic background radiation, or CBR. That is just particles coming from pulsars, quasars. It's just coming from everywhere. Can't really predict it. It's just kind of always there. You also get high energy particles from the sun, especially like solar flares and that kind of stuff. Can be very dangerous to satellites. Many satellites have been knocked out by solar flares. And also, the Earth has this lovely magnetic field that protects us here on the Earth from a lot of these high energy particles, but it just traps them in the Van Allen belts. And when satellites are flying around the Earth, they then end up flying right through the Van Allen belts over and over and over again. And that really starts to wear down any satellite, any mission, CubeSats especially, just because your margins are so tight. And I wanted to, you can even see on like the NASA Houston mission control, they even have a little box on there just highlighting the South Atlantic anomaly, just the fact that the Earth is tilted and it's got the the iron core. There's kind of a hot spot for where a lot of these particles get collected, and they keep track of every single time the ISS and the little squishy humans on board go through that, kind of keep a tally, because it does add up over time, and it's just something we have to think about. When you get down to like the computer level, a lot of times the things we're looking at are called single event upsets. This is a state change in memory just caused by a high energy particle crashing into the little transistors in your circuit board, in your processors. And sometimes you can get multiple bits that get flipped in memory, which is not great, but usually not destructive. So we can usually fix that, and there's techniques for detecting that your data has been corrupted. You start getting latch ups. Those are a little bit worse. Those are transistor is held to ground and you can't release it without power cycling the computer. That's a little bit worse. There's also total ionizing dose, or TID. We talk about that in terms of it's kind of like the odometer for a mission. It's all your parts on a satellite will have some TID rating, and you design around, okay, we're going to be flying in this orbit and through the Van Allen belts. We're going to go through it 30 times in the mission, and you add up how much radiation you think your satellite's going to experience. Um, the hard part about TID is there is very little research out there about what hardware is actually rated for in terms of ionizing dose, um, because it's not really a thing we worry about on Earth, and it's starting to become more common, actually, as so the reason radiation is actually becoming more of a problem within the last, say, 20 years of space travel. This is really not a problem almost at all back in the Apollo days, because we're making transistors so small. And as you make the transistors smaller, the energy it takes to sort of short across the PN junction of a transistor is getting lower and lower and lower. So things like for Apollo, everything was just so big, it would take forever before anything would have a radiation damage to it. But now you can get CubeSat missions that will conk out after a couple hours or a day, depending on the orbit they get launched into. Um, there's also a technique to mention called a triple modular redundancy, or TDR. Basically, the way the aerospace industry handles a lot of these single event upsets is just do everything 3 times and vote on what the 3 processors did. Um, and, this is usually done nowadays. It's done with a lot in FPGAs because it's basically a circuit board you can program. It's a processor you can program into being a circuit. It's weird, but they lend themselves really well to just sort of rebuilding themselves after they get hit by radiation. Um, and then try to write stuff to memory with error correction and parity check, just to try to detect and be able to correct memory errors if you can. And it's this one is still kind of a there is no actual solution to radiation hardening that will last forever. The Curiosity rover back in 2013, they had to swap over to their B-side computer because their A-side computer has so many memory faults and so many logic core faults that it's more beneficial to just use the backup computer. And I think actually since 2013, I want to say they've swapped back to the A-side computer because yeah, it's degraded, but now B has degraded more than A. Um, so sometimes you just bring 2 computers along and just swap around from one to the other. Stuff starts to wear down. Um, something something also really interesting, if you guys are not aware of it, radiation damages mechanical systems too. You look into the Kepler Space Telescope and Fuse and Dawn. Scott Manley, YouTuber, talks about space travel, has a really good video on this. The short of the long of it is they are finding that reaction wheels with bearings inside of them are failing at a really high rate, higher than they expected they would, and it's actually because the ball bearings are building up charge from all of the high energy particles, and eventually they arc to the rest of the satellite, and it's slowly arcing, it's slowly wearing down the bearings, which I thought super cool. They make like ceramic bearings and stuff now too, but that's super neat. And then lastly, I just wanted to mention thermal systems is also a really cool area to go into, dealing with these super high and low temperature swings. Every 90 minutes when you're in low Earth orbit, your satellite is freezing, it's burning, it's freezing, it's burning. And not only does that wear down the electronics and the batteries, but it also causes the whole structure to thermal cycle, which is one problem when you're talking about the structure wearing down and getting micro cracks and stuff, but also when you have a comm system and you say you have a dish antenna and you have to be really precise with how you're pointing it, you'll actually get pointing errors due to the satellite kind of tweaking back and forth as it heats up and cools down. Um, and it's super interesting. I would like to get more into spacecraft thermal design. That's kind of like eventually I'm going to try and work my way that direction someday. Um, yeah, that's all I have. I figured I would just come and rant to you guys a little bit. Um, and yeah, do you guys have any questions you wanted to ask me while I'm here?
I think we can definitely take some. We'll start with the room and then transition online if anyone online has any. But before we do, I just want to say this was really cool. Thank you for stepping up to the plate and like sharing your passion and knowledge on this with us. And I think, like I said, we have folks in here that might have a little bit of a ham radio background, some folks in here that might have a little bit of a SAT background, but there's also a lot of people here that are just curious and wanted to come get exposed to something new. So yeah, thanks to all of you for being here as well. This is really exciting.
Yeah,
Okay.
thank you all.
The mic situation isn't great, so if anyone has a question, we'll try to ask it from here, and then if Thomas can't hear you, we'll have you sit down here and we'll ask it again. So, does anyone have any questions? Yes.
With bits getting flipped or transistors getting locked to high at much higher frequency than in the past, is there more of a focus on, I don't know, manufacturing larger transistor components, or is that not really a thing?
Yes. Well, it depends. It all goes in the trade space of designing a satellite mission. You can work with a company and develop a custom processor, but at the same time, there's a push to try to use off-the-shelf components. Back in the Apollo days, they made everything from scratch, but now it's more financially viable to just buy 3 processors that are probably not going to last and just, first one burned out, use another one. And if you make your transistors bigger, you can fit fewer of them, so you have weaker processors. That's why you see, part of the reason why you see like the Mars rovers, I think Perseverance, the most recent one with the helicopter, I think the processor on that one is akin to like a 1990s Compaq desktop, the little white beige. Part of that is the processor is around long enough that we know kind of how it does just on Earth, and it's built back in the older days when transistors were just bigger. So you kind of see some of that. That's why they tend to use older equipment for satellites, not because they asked for anyone to make a bigger transistor processor, but it's what they had when they started designing it, and it just happens to work better. So, and yeah, if you had the money, go ahead, make your own processor. But a lot of people don't.
Any other questions? Yeah.
What's your favorite thing about working with objects in space?
Probably, yeah, probably. I really like designing satellites. I'm not super a hit of a science nerd, so I don't care personally too much about exploring the cosmos. I think it's really cool to do, but I really want to figure out the how. Like, how do you get that rover on Mars? How do you do it? Which I think is really cool. And with spacecraft, I really enjoy just it's the most pure form of engineering I think that there is in like aerospace, because there's zero hand holding. When the satellite's in orbit, you can't pull a brake. You can't just have it stop and sit there or like look at it and go, oh, what's wrong? Like, when it fails, it just fails, and there's nothing you can do about it. You should look into one of my favorite stories is so we sent back in the space race days, the U.S. we focused on Mars. That was our big thing. The Soviet Union, they focused on Venus because there was a lot of thought back in the 50s and 60s that Venus, when you get past the clouds, might be this like oasis, paradise. So the Soviets actually sent a probe to Venus, and it, launched. It was going into the atmosphere, and they got readings back, and they watched the pressure rise and rise as the atmosphere got thicker and thicker, and then it just never stopped until it just like turned off. And they were like, "Huh. Well, that was really strange. Let's just go throw another one." And so they sent another probe, and it came down, and it actually went further and further, and they were like, "Wow, it hasn't hit the bottom. It hasn't hit land yet, but it's like an Olympic swimming pool, like under the water pressure, and it's still in air. That's weird. Let's send another probe." And so they sent one, and they said, "Okay, we're gonna just go straight through the atmosphere and try to crash into the surface as fast as we can." And they actually, if I remember right, they didn't even have a parachute because the air was just so dense. They just let the air slow them down. And they finally got a probe to survive because I think that one that it went straight through the atmosphere and then melted. They got one to finally go down and land on the surface, and it only survived on the surface, I think, for like 30 minutes before everything just melted. But they brought a camera with them. And so they were like, "All right, we're going to get a picture from the surface of Venus." And they took a picture, and it came back, and it was just black. The reason was the lens cap didn't come off. So they sent another probe and did this whole, like, all the way, this giant travel through the dense atmosphere, go straight down, crash into the surface, unfolded, lens cap didn't come off again. So they sent a third one, and it traveled all the way through space, back in, did the whole thing, crashed on the surface, and like opened up, and they had an explosive charge to just detonate and just shatter the lens cap off. And they did that, shattered it off, and they got a pic, and they finally have like the only picture of Venus, the surface of Venus, that anybody has ever taken. And they were like, "Oh, that's awesome. Let's go use the soil. While we still have time, let's go test the soil. See what the soil's like." Deployed the little soil probe, and they were like, "Man, this is a really weird material. It's really hard, but kind of like melty." It turns out they were actually spearing into the lens cap. So like they were soil sampling the lens cap. Like, you can't make that stuff up. Like, I love space for stories like that, like that kind of engineering challenge you have to overcome where sometimes you're just like, "Okay, sure, whatever." That's what gets me excited about space. Yeah, stories like that.
That's awesome. Okay. Maybe if anyone else in the audience has one, we'll ask, then we'll ask if anyone online has one. No? Okay, cool. That is such a good story. Oh my gosh. Anyone online have a question? If you do, you can raise your Microsoft Teams hand. Give it a second. Seems like maybe not. Okay. I think that means we're done. Thomas, thank you so much. This was a super, super cool talk. I think that we got like a lot of breath here, right? But hopefully this kind of like gave people a little bit of like an intro or a sampler into like some of the really cool things that are going on in this space. Pun not intended, but maybe I should have intended it. Yeah. Anyway, yeah, I'm sure Thomas agrees. Come work in space. Come work on satellites. It's awesome. Let's do it.
Yeah.
Okay. Anyway, Thomas, I'll follow up with you later. But yeah, thank you so much for talking with us. This was awesome.
Yeah, thanks. I know I kind of just like rambled, because it's just like a giant topic. There's like so many things to cover. Some people will, like people at Goddard that I've run into, they've been at NASA for 40 years, and all like I know a guy, like, all he has ever done is parachutes. That's all he does. His entire, for like 40 years, it's just parachutes. And the fact that there is enough nuance in just parachutes that someone could spend 40 years working on it is so hard to convey, of just how enormous of a challenge space travel is. And so, yeah, I come to just ramble and just kind of spread some cool things I've learned that got me excited. Hopefully you guys get excited about space too.
Yeah, that's fantastic. Okay. Thank you so much. Thanks for coming, everybody. Bye bye.
Thanks, everyone. Bye.